What if everything we know, every galaxy, every planet, every atom, every law of physics, is just a small island in an endless ocean of unknown existence, stretching beyond comprehension, beyond visibility, and beyond the very concept of space and time itself? Picture standing on the edge of the known universe, where light from distant stars fades into darkness, not because there's nothing there, but because the cosmos simply hasn't had enough time to deliver its secrets to us. You are looking into the past, peering 13.8 billion years back with every photon that reaches your eye. Yet what truly grips the imagination is not what we can see, but what we can't, the invisible expanse beyond our cosmic horizon that refuses to be mapped or measured. This is not the edge of the universe, but the limit of our observation, the frontier where science meets mystery, and where speculation gives birth to some of the most profound theories ever conceived by human minds. Are we living in a bubble within a much grander multiverse? Our universe just one of an infinite ensemble, each with its own distinct physical laws and possibilities? Or is the universe infinite in all directions, continuing forever with galaxies beyond galaxies, stars beyond stars, all unreachable and forever unknown? Maybe, just maybe, space itself folds in ways our brains aren't wired to understand, looping back through higher dimensions like a cosmic Mobius strip, where the end connects to the beginning, and our place in it is less a dot on a map and more a repeating rhythm in a symphony of space-time. The truth is, we are prisoners of light, bound by the speed at which it travels, and thus imprisoned within a 93 billion light-year-wide cell, whose walls expand faster than any message or probe we could ever send. Our cosmic vision is not limited by instruments, but by the fundamental nature of reality. And yet, we strive, we ask, we theorize. Scientists simulate what lies beyond, using the mathematics of general relativity and quantum field theory to pierce the veil, to catch glimpses of the greater whole, to answer questions we can barely articulate. Some suggest that beyond the observable universe, there exists more of the same, more stars, more dark matter, more black holes, continuing endlessly like pixels repeating across an infinite screen. Others propose that the very fabric of the cosmos might change, that constants like gravity or the speed of light might be different in distant domains, that physics itself may be local, not universal, confined to this particular cosmic neighborhood. If the Big Bang wasn't the beginning of everything, but merely the beginning of our part of the universe, then what came before, or what lies beyond, could redefine existence itself. Quantum mechanics hints at a multiverse birthed from every probabilistic event, with infinite realities diverging every second, each one forming a new universe with different outcomes, different versions of you, of Earth, of history. Inflationary theory, now a cornerstone of modern cosmology, suggests that the rapid expansion of space in the early universe never stopped completely, but continued on in other regions, creating an eternal fractal foam of universes, in which ours is just one bubble among countless others. And yet, despite the vastness of it all, there remains the haunting possibility that beyond the observable universe lies nothing, not emptiness, not a continuation, but a true void, an absence of space, time, and being, where the concept of location no longer applies. Such nothingness isn't just darkness, it's the non-existence of even the possibility of darkness, a realm untouched by dimension or causality. That kind of boundary terrifies and fascinates, for it challenges our deepest assumptions not only about cosmology, but about existence, consciousness, and the human drive to explore. We stand as tiny beings on a pale blue dot, as Carl Sagan described, gazing into an endless night with minds powerful enough to model the unobservable, to argue over the fate of infinities, and to question the nature of the laws that govern reality. And perhaps that's the most miraculous truth of all. Not that the universe might be infinite, but that we, finite creatures with finite lives, dare to contemplate it. We invent tools that let us see billions of years into the past, machines that measure the subtle echoes of the Big Bang, telescopes that capture photons older than Earth itself, all to feed the hunger for understanding what's out there and what lies beyond. Every discovery raises deeper questions. Every answer opens new doors. And yet the veil never fully lifts, only thins enough to glimpse the shadows behind it. If dark energy is accelerating the universe's expansion, as the evidence suggests, then the distant galaxies we see today will someday vanish from view, pushed beyond our reach by the relentless stretching of space itself, leaving future astronomers with an empty sky and a forgotten origin. But today, we remember. Today, we question. Today, we dream of what's past the edge. Are there other beings asking the same questions, staring into their own cosmic horizons, wondering if they are alone or if their observable patch is just another pixel in an unfathomable mosaic? Or is our universe a unique miracle, one-off and singular? A bubble of improbability suspended in a void where nothing else can form? Either answer carries consequences too vast to absorb in a single lifetime, and yet we try. We build narratives around these possibilities, using mathematics as our language and curiosity as our guide. Even if we can never travel there, never see it, never touch it, what lies beyond the observable universe defines us, because it reminds us that we are part of something greater, not just physically, but philosophically. The more we learn, the more we realize how little we understand, and that humility, paired with the unstoppable will to uncover what's hidden, is perhaps the most beautiful trait of all in this strange, expanding story called reality. You've likely stood outside at night, looked up at the stars, and felt something stirred deep inside you, an emotion without a name, a mixture of awe, insignificance, wonder, and longing all wrapped together. That feeling is not a coincidence, not just a trick of poetic imagination. It is rooted in something profoundly human, the innate desire to understand where we come from, what we're a part of, and where we might be going. When we ask, what lies beyond the observable universe, we are not just exploring a scientific question, we are brushing up against the very boundaries of human experience, purpose, and meaning. In a world overflowing with noise and distraction, there is something powerfully grounding about contemplating the cosmos. It silences the chaos, not with answers, but with perspective. And in that silence, a deeper connection is formed not just to the stars, but to ourselves and to each other. Caring about what lies beyond isn't about mastering equations or memorizing distances. It's about confronting the unknown with courage and curiosity. It's about daring to imagine that the universe is larger, older, and more complex than anything we've ever encountered, and accepting that within its vastness, we are both impossibly small and immeasurably significant. There is a strange comfort in realizing that the atoms in your body were forged in ancient stars, that your blood carries the remnants of stellar explosions, that your very being is a byproduct of cosmic evolution. You are not separate from the universe, you are of it. Every breath you take is an echo of time, every thought a ripple in the great unfolding of space and energy. That connection, the direct line between your consciousness and the universe's birth, should evoke more than just intellectual fascination. It should evoke emotion, reverence, even love. Because to understand the cosmos is, in a way, to understand ourselves. And the moment we glimpse the edge of our observable universe, we are forced to ask not just, what's out there? But what does it mean that we can even ask this question? Why do we care? Because the cosmos reflects our inner landscape. The darkness between the stars mirrors the unanswered questions in our minds. The stretching of galaxies echoes the stretching of our own hopes. The mysteries of dark matter and energy parallel the mysteries of human consciousness. And when we realize that our instruments are too limited, that light itself takes billions of years to travel across the void, that there are places we can never reach, something within us grieves that limit, even as it burns brighter with curiosity. There is beauty in the boundaries of what we know. Standing at the edge of the observable universe is like standing at the edge of a vast, unexplored ocean. You can see the water stretching into the horizon, but you know there are depths you'll never touch, lands you'll never discover, truths you'll never fully grasp, and yet you dream of them. This act of dreaming, of imagining the infinite, is what makes us human. It's what fueled the myths of ancient storytellers, the calculations of astronomers, the silent prayers of people staring up into a sky that never speaks back. The void beyond the stars is not empty, it is full of the questions that define our very existence. What is time? What happens when we die? Is there purpose? Are we alone? These questions are not separate from cosmology. They are embedded within it. Every inquiry into the structure of the universe is also an inquiry into who we are and why we're here. And in those questions lies the full range of human emotion, from awe to terror, from wonder to despair, from hope to transcendence. Fear plays a role too. There is a deep and ancient fear that creeps in when we contemplate the infinite. It's the fear of insignificance, of being lost in an unfeeling universe, of having no center, no control, no greater plan. If the universe is truly endless, with billions of galaxies each containing billions of stars, and perhaps billions of universes beyond that, then what are we? Just a fluke of chemistry on a pale blue dot? This existential vertigo is hard to bear. It's the feeling that perhaps nothing we do matters, that life is temporary and meaningless against the backdrop of eternity. But here's the paradox. The same fear that makes us feel small also opens the door to something deeply empowering. If we are tiny and temporary, then every moment we're alive becomes infinitely precious. If the universe doesn't assign us meaning, then we are freno. We are responsableto, create meaning for ourselves. Our emotions, our stories, our connections with others, they become not just distractions from the void, but answers to it. Against the cold silence of space, our laughter, our love, our struggles become acts of defiance, declarations of life in a cosmos that neither notices nor judges. And then there's the wonder, their childlike wonder that nothing else in life can quite replicate. To realize that we are living at a moment in history where we can look back in time, where we can detect the faint glow of the Big Bang, where we can model the birth of galaxies and the dance of particles that emerge seconds after time began, that is a gift so extraordinary, it feels like magic. We are not just spectators in the universe. We are the universe becoming aware of itself. Consciousness, imagination, the ability to ask questions about existence, these are not evolutionary accidents. They are the universe's way of seeing itself. And so when you look up at the stars, when you feel that pull toward the unknown, what you're really feeling is the universe pulling you home, calling you to remember what you already are, a spark of stardust with the power to wonder, to feel, to care. That is why people should care, not because they need to memorize facts or build telescopes, but because the act of caring connects them to something eternal. Caring about what lies beyond the observable universe is an act of hope. It's a belief that there is always more to discover, always more to understand. And that belief isn't limited to science. It shapes how we approach life. It teaches us that limitations are not dead ends, but invitations to grow. It shows us that mystery is not a failure of knowledge, but a playground for imagination. It reminds us that while we may never know all the answers, the pursuit of understanding is itself a kind of salvation. For those who struggle with depression or anxiety, for those who feel lost or trapped in the narrow corridors of daily life, the universe offers perspective. You are part of something vast and ongoing. Your problems, while real, exist in a context so wide and ancient that even your pain becomes part of a story too grand to fully comprehend. And that story includes every one of us, whether we are scientists or poets, children or elders, skeptics or believers. We are all born into the same mystery. We all share the same sky. What lies beyond the observable universe may never be known, but what lies within us, the hunger to know, the ache for connection, the courage to face the infinite that is more certain than gravity. It is etched into our DNA, passed down through generations of explorers, dreamers, philosophers, and visionaries. The same wonder that drove our ancestors to carve constellations into cave walls is the wonder that drives us to launch telescopes into space. The same fear that once whispered of gods and monsters in the dark is the same fear we feel when confronting the possibility of cosmic isolation. These emotions are not outdated. They are eternal, and they are necessary. Because without them, we would never look up. We would never ask what's out there. We would never care about the edge. So, if you've ever felt small beneath the stars, if you've ever wondered what's beyond the reach of our eyes, if you've ever felt joy and terror in the same breath while contemplating the void, then know this: you are not alone. You are part of a long line of humans who dared to imagine more, who dared to believe that in the vast unknown there was something worth seeking. And whether we ever reach the edge of the universe or not, whether we ever answer the great questions or not, what matters is that we keep asking, that we keep looking, that we keep feeling. Because in the end, the story of the universe is not just a scientific journey, it is an emotional one. A story of longing and love, of fear and discovery, of the incredible power of a species that, against all odds, looked into the dark and said, "I want to know. I need to know. I care." Thousands of years ago, when early humans gazed up at the night sky, they saw patterns, not galaxies. The stars became stories, myths, and gods, woven into the fabric of cultures across every continent. To the ancients, the sky was a dome stretched over a flat earth, and celestial bodies moved with purpose and divinity. The Babylonians, Egyptians, Greeks, and Chinese all developed sophisticated systems of astronomical observation long before the invention of the telescope. But their understanding, though brilliant for its time, remained geocentric. The Earth was the center of creation, and everything else, the moon, the Sunday, the stars, revolved around it. This view, formalized by the philosopher Ptolemy in the 2nd century AD, endured for over 1,000 years, shaping not just science, but religion, politics, and philosophy. Then, during the Renaissance, a revolutionary shift began. In 1543, Nicolaus Copernicus published De Revolutionibus Orbium Coelestium, proposing a heliocentric model of the universe, placing the Sunday at the center. His work, though controversial, cracked open the door to a new understanding of the cosmos. A century later, Galileo Galilei used a telescope to observe the phases of Venus, the moons of Jupiter, and the rugged surface of the moon, empirical evidence that supported Copernicus and challenged centuries of dogma. The universe, it seemed, was not built around us after all. Isaac Newton's publication of Principia Mathematica in 1687 further transformed our grasp of the cosmos. With his laws of motion and universal gravitation, Newton showed that the same physical laws governed both the fall of an apple and the orbit of the planets. Suddenly, the universe became a clockwork machine, rational and predictable, its mechanics governed by mathematics. But it wasn't until the 20th century that our view of the universe expanded beyond imagination. Albert Einstein's theory of general relativity, published in 1915, replaced Newtonian gravity with a model of space-time curvature. Gravity wasn't a force, but a warping of the very fabric of space and time by mass and energy. This elegant theory would later be tested and confirmed by astronomical observations, such as the bending of starlight during a solar eclipse. Around the same time, astronomers were beginning to question the nature of so-called nebula, fuzzy patches of light in the sky. In the 1920s, Edwin Hubble used the Mount Wilson Observatory to study these objects and discovered something astonishing. Some nebulae were not clouds within our galaxy, but entire galaxies themselves, millions of light years away. Even more groundbreaking was his discovery that these galaxies were moving away from us, and the farther they were, the faster they receded, phenomenon now known as Hubble's law. This provided the first observational evidence for an expanding universe, leading to the revolutionary idea that the universe had a beginning, a moment of creation known today as the Big Bang. The Big Bang theory proposed that the universe began as a singularity approximately 13.8 billion years ago and has been expanding ever since. In 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, CMB radiation, a faint glow permeating the universe, which was soon identified as the thermal afterglow of the Big Bang itself. This discovery cemented the Big Bang as the dominant cosmological model, marking a turning point in our understanding of cosmic history. The CMB provided a snapshot of the universe when it was just 380,000 years old, a baby picture of the cosmos that has since been studied in exquisite detail by satellites like COBE, WMAP, and Planck. These missions revealed subtle temperature fluctuations in the CMB that encode information about the early universe's density, composition, and geometry. In parallel, the late 20th and early 21st centuries saw remarkable advances in space exploration. The launch of the Hubble Space Telescope in 1990 opened a new era of deep space observation, capturing images of galaxies billions of light years away, and helping to refine our understanding of cosmic expansion. Robotic missions like Voyager, Cassini, and the Mars rovers transformed our knowledge of the solar system, while ground-based observatories and new telescopes like the James Webb Space Telescope continue to peer deeper into the universe than ever before. These discoveries led to profound theoretical developments. In the 1980s, physicist Alan Guth proposed the theory of cosmic inflation, suggesting that the universe underwent a brief period of exponential expansion, a fraction of a second after the Big Bang. Inflation solved several cosmological puzzles, such as why the universe appears so homogeneous on large scales and why its geometry is so flat. It also introduced the possibility of a multiverse, a vast ensemble of universes born from quantum fluctuations in the early cosmos. Around the same time, the mysterious nature of dark matter and dark energy emerged. Observations of galaxy rotation curves and gravitational lensing indicated that visible matter accounted for only a small fraction of the universe's mass. The rest dark matter exerted gravitational influence without emitting light. In 1998, two independent teams discovered that the expansion of the universe was not slowing down, as expected, but accelerating. This led to the introduction of dark energy, a repulsive force that now accounts for nearly 70% of the universe's energy density. These discoveries reshaped the cosmic inventory and introduced a new mystery. We understand only about 5% of the universe, the rest being dark and largely unknown. Central to modern cosmology is the concept of the observable universe. While the universe itself may be infinite, the observable universe is finite. It represents the region of space from which light has had time to reach us since the beginning of the cosmic expansion. Because space itself has been expanding, this radius is not 13.8 billion light-years, but approximately 46.5 billion light-years, making the observable universe about 93 billion light-years in diameter. Beyond this lies the unobservable universe, a realm forever hidden from us by the finite speed of light and the accelerating expansion of space. This boundary is not a physical wall, but a horizon set by the limits of causality. We can never know what lies beyond it, and yet, through mathematics, theory, and indirect inference, we attempt to describe it. The idea that our cosmic vision is bounded by the speed of light and the passage of time has profound philosophical implications. It places a limit on what we can know, but also invites speculation and exploration. The milestones that brought us here: Copernicus's heliocentric model, Galileo's telescope, Newton's laws, Einstein's relativity, Hubble's expansion, the discovery of the CMB, the proposal of inflation, the unveiling of dark matter, and dark energy mark a step in a journey that has transformed humanity's understanding of its place in the universe. These discoveries were not just scientific achievements, but paradigm shifts that altered our worldview. From thinking we were at the center of the cosmos, to realizing we orbit an average star in an unremarkable galaxy among billions, the trajectory of cosmology has been one of growing humility and awe. And yet, this very smallness, this sense of cosmic insignificance, is matched by our capacity for thought and wonder. Our species, forged in the crucible of stardust, has built instruments that peer across time and space, decoding the birth and fate of everything. We have mapped the structure of the cosmic web, a vast network of galaxies and voids spanning the observable universe, shaped by gravity and the remnants of quantum fluctuations from the earliest moments of time. Humanity's journey through cosmological understanding is not merely a chronicle of facts, but a testament to our enduring curiosity. From the first astronomers tracking the movements of stars with nothing but their eyes and intuition, to the modern cosmologists using space-based observatories and particle accelerators, our quest has been to answer the oldest questions. Where did we come from? What is the nature of reality? Are we alone? Each scientific milestone has added a piece to the puzzle, even as the picture continues to expand. As we develop new technologies, gravitational wave detectors, next-generation telescopes, quantum simulators, we stand on the cusp of even greater revelations. Perhaps one day we will understand the nature of dark matter and dark energy, confirm the existence of other universes, or glimpse what lies beyond our observable horizon. Until then, we continue to explore, to question, and to marvel. The observable universe is both a boundary and a beacon, the edge of our knowledge and the beginning of our wonder. Through the lens of science, we transform the sky from a canopy of lights into a window to eternity, a vast arena where space and time themselves began. And though we may never know the full story, we are, astonishingly, a part of it. Have you ever stopped to ask yourself what it truly means to exist? Not just as a human being walking on Earth, but as a sentient creature in a universe that might be infinite, eternal, or even one of countless others. What do you believe lies beyond the farthest thing we can see? When you look at the stars at night, are you looking at the edge of something or just the beginning of something far greater? These aren't idle questions. They are the foundation of a conversation that has driven science, philosophy, and art for millennia. Because when we ask what lies beyond the observable universe, we are asking more than a scientific question. We're asking what kind of reality we live in, what it means to know something, what it means to be alive in the face of endless possibility. This isn't just for astronomers or physicists. It's for anyone who has ever looked up and wondered. It's for anyone who has ever felt the pull of the unknown. It's for you. Imagine that we suddenly discovered conclusive evidence of another universe, a cosmic neighbor, with different physical laws, perhaps even different forms of matter and time. How would that change the way you view yourself? Would you feel smaller, or would you feel like part of something grander? If the observable universe is just a small patch in an infinite multiverse, then does that change the significance of your choices, your values, your dreams? Would your sense of purpose grow stronger or weaker in the face of such revelation? Now imagine we discovered the opposite, that beyond the observable universe, there is nothing. Not empty space, but the absence of even space itself. That the universe has an edge, and we are drifting toward it. Would that make you feel isolated or safe? Would it make the universe more mysteriouser, more terrifying? These are not abstract hypotheticals. They are emotional truths wrapped in scientific possibility, and they are worth thinking about deeply. Why does this mystery matter? Because it forces us to confront the limits of what we know and to question the frameworks we've built to understand everything else. Most of us walk through life assuming we understand the basics. The sky is above us, the earth is beneath us, time moves forward, and space is a silent backdrop to all our actions. But what if time isn't linear? What if space curves back on itself? What if reality is built on laws that only apply here, in our little corner of the cosmos, and the rest is governed by something so alien we can't even describe it? Every time we push the edge of the observable universe, we are redefining what it means to be real. And if we are serious about understanding ourselves and the world around us, we can't ignore that. The observable universe is not a map, it's a mirror. It reflects our hopes, our fears, our assumptions, and our imagination. The better we understand it, the better we understand ourselves. Think about this. What if the next generation of telescopes or gravitational wave detectors discovers a signal from another universe? What if we pick up a cosmic fingerprint that doesn't match anything we've ever seen or ripple in the cosmic microwave background? A strange anomaly in the distribution of galaxies, or an unexplained burst of energy from the deep void? How would that affect religion, politics, science, and art? Would we rewrite our textbooks? Would we rewrite our myths? Would we become more united as a species or more fractured? The impact of such a discovery would ripple across every level of society. It would challenge our certainty, force us to adapt, and maybe, just maybe, bring us closer together. Because in the face of the unknown, we are all equally small, but we are also equally capable of wonder. This is your invitation not just to learn, but to engage. Ask yourself the hard questions. What do you believe about the nature of reality? Do you think the universe has an edge? Do you think there are other universes, other versions of you, other civilizations asking these same questions? If you could send a message beyond the observable universe, what would it say? Would it be a question? A warning? A poem? And if you could receive a message from beyond, what would you hope it said? Would it bring comfort or chaos? Would it validate your beliefs or shatter them? These questions aren't designed to have answers. They're designed to open you up to stretch your thinking, to awaken your curiosity, to remind you that the most important part of science is not the facts, but the questions. And you're not alone in this. There's a global community of thinkers, dreamers, scientists, and storytellers asking the same questions right now. People in every culture, every language, every belief system are trying to make sense of the same stars. So why not join the conversation? Share your thoughts. Ask others what they believe. Talk to your friends, your family, your teachers. Start a discussion group. Create art, write stories, make videos. Build something inspired by the cosmos. Use the universe as a canvas for your imagination, because the edge of the observable universe isn't a wall, it's a door, and every time someone asks, "What's out there?" we push that door open a little more. The beauty of this mystery is that it belongs to everyone. You don't need a PhD in astrophysics to participate. You just need the courage to wonder, the courage to admit that you don't know, the courage to look into the dark and keep searching. That's what exploration is, not knowing where you're going, but going anyway. And that's what makes the question of the observable universe so powerful. It reminds us that we're still explorers, still travelers, still reaching for something greater. In an age where so much feels known, measured, and controlled, this mystery remains unclaimed. It is a vast open space waiting for new ideas, new voices, and new questions. So here's the challenge. What's your question? What do you want to know about the universe? What keeps you up at night? What fills you with wonder? Don't let the vastness intimidate you, let it inspire you. Let it push you to think bigger, feel deeper, dream wilder. The universe is not just out there, it's within you. Your curiosity is not separate from the cosmos. It is a function of it, a natural extension of the same forces that create stars and galaxies. And every time you ask a new question, you become part of the universe's story. You become a participant in its unfolding. If there's one thing the mystery beyond the observable universe teaches us, it's that there is always more. More to learn, more to feel, more to imagine. Reality is not fixed, it's expanding. Just like the cosmos. And so are you. Every new idea, every new perspective, every new question is a step into the unknown. And the unknown is not something to fear, it's something to explore, to celebrate, to share. So go ahead, ask the big questions, engage in the great conversation, be part of the mystery. Because the universe isn't just something you observe, it's something you belong to. And that means you have a voice in its story. Use it. Space is not silent. It hums with radiation, pulses with gravity, and breathes in the slow rhythm of galactic drift. If you could close your eyes in the vacuum beyond Earth and feel with something deeper than skin, you'd sense the movement of things too vast for the mind to grasp and too slow for a single lifetime to witness. Picture yourself suspended in the emptiness between stars, far from the warmth of any sun, where distances are measured not in kilometers, but in light years. And even the speed of light feels agonizingly slow. Around you, a vast canvas unfolds, a backdrop, a velvety black, interrupted by pinpricks of fire, each one a sun, many of them with planets, some perhaps with life. Turn slowly, and in the far distance, you'll see the great spirals of galaxy, hundreds of billions of stars dancing together, bound by invisible threads of gravity, their arms twisting in luminous arcs across the deep dark. And, further still, between these galaxies, stretch the voids, regions of almost unimaginable emptiness, where gravity seems to have lost its grip, where entire galaxies are rare, and the silence deepens. But even this emptiness is not truly empty. It is filled with unseen forces, dark matter, weaving an invisible web through the universe, pulling galaxies into filaments and nodes, shaping the grand architecture of the cosmos. This dark matter doesn't shine, reflect, or glow, yet its presence is undeniable. It sculpts the structure of clusters, bends the path of light from distant objects through gravitational lensing, and tips the scales in equations we've only recently learned how to write. Then there is dark inner stranger still, a mysterious force not pulling, but pushing, stretching space itself, so that galaxies are not just drifting apart, but accelerating away from each other. This force is quiet, undetectable by direct means, but it dominates our universe, accounting for nearly 70% of its total energy. It turns the cosmos into a balloon that keeps expanding, faster and faster, carrying distant galaxies out of view, erasing them from our future skies. And as we stare into this accelerating night, we begin to understand the universe is not static, not stable, not even permanent in the ways we once imagined. The tone of the cosmos is not horror, nor peace, it is sublime mystery, wrapped in a language of light and gravity. In that vast theater, certain names echo like constellations themselves. Albert Einstein, whose theory of general relativity became the key to understanding the shape of space-time, laid the foundation for modern cosmology with equations that describe how mass and energy curve the very fabric of the universe. Edwin Hubble, who peered through the 100-inch Hooker telescope on Mount Wilson and discovered that galaxies were fleeing from us, showed that the universe was not eternal and unchanging, but expanding. Alan Guth, whose theory of cosmic inflation explained why the universe is so flat, so uniform, and so vast, envisioned a moment of explosive growth that happened faster than the blink of an eye. And Vera Rubin, who quietly revolutionized our understanding of galaxy rotation, helped uncover the invisible scaffolding of dark matter. These pioneers, among many others, didn't just make discoveries, they reshaped reality. Now imagine the setting not from Earth, but from the edge of the observable universe. Imagine standing on a platform, a trillion light-years from our planet's impossible vantage point, but indulge the thought and, looking back toward our galaxy, which by then would be a dim flicker in a sea of dark energy. Around you, the landscape is composed of ancient light. The cosmic microwave background bathes everything in a faint glow. The last whispers of the Big Bang still echoing across space. But this echo is not uniform. It shimmers with tiny fluctuation shot and cold spots that tell the story of the early universe, of quantum ripples stretched to cosmic size, of the seeds from which galaxies grew. You see the cosmic web, a sprawling network of matter that forms the largest structures in existence, with filaments stretching hundreds of millions of light-years, dotted with galactic clusters where thousands of galaxies swarm like fireflies in the night. In the gaps between these clusters are the great voids regions, so vast and empty, they challenge our understanding of balance and symmetry. These voids are not mistakes. They are features of a universe in dynamic equilibrium, shaped by invisible forces and ancient initial conditions. Within these structures, galaxies themselves are stories. Spiral galaxies spin like cosmic pinwheels, with arms glittering in blues and white shot, young stars burning briefly and brightly. Elliptical galaxies glow red and silent, filled with ancient stars, long past their days of creation. Dwarf galaxies, strange and chaotic, orbit larger neighbors like moons on cosmic scales. Some galaxies collide, merging in slow-motion cataclysms that last millions of years, triggering waves of starbirth and feeding the supermassive black holes at their cores. These black holes, millions or billions of times the mass of the Sunday, sit at the centers of galaxies like sleeping giants, occasionally waking to emit jets of high-energy radiation that can outshine their entire host galaxy. The galaxies themselves are not scattered randomly, but form a coherent pattern like bubbles on the surface of boiling water, like neurons in a brain far beyond human scale. And still, deeper questions beckon. What happened before the Big Bang? Was there a before? Are there other universes beyond our cosmic horizon, inaccessible not just in practice but in principle? Could there be other dimensions, curled up at microscopic scales, unseen but influencing the gravity that governs galaxies? These questions are not idle speculation. They are the current frontiers of physics, explored not just by thought experiments, but by satellite observations, particle accelerators, and massive simulations run on supercomputers that mimic the evolution of the universe from its first microseconds to its present grandeur. Scientists today work at the intersection of theory and observation, using instruments like the James Webb Space Telescope, the Euclid mission, the Vera Rubin Observatory, and gravitational wave detectors like LIGO and Virgo to probe deeper than ever before. These machines don't just take pictures, they decode the ancient language of the cosmos, turning photons into data and data into understanding. In this setting, every discovery is a key turning a lock. We discover an exoplanet orbiting a distant star, and suddenly, we imagine life in another corner of the galaxy. We detect a gravitational wave from the collision of black holes, and suddenly, the universe becomes audible. We measure the polarization of the cosmic microwave background, and we glimpse the fingerprints of inflation. Each of these insights is not just a step forward in knowledge, it's a shift in atmosphere, a change in how we feel about existence itself. The awe is not only in the scale, but in the elegance, the fact that so many phenomena, from the orbits of planets to the structure of galaxy clusters, can be described by the same fundamental principles. The more we learn, the more the universe reveals its underlying unity, its deep symmetry, and yet, its irreducible strangeness. There is also humility in the atmosphere of cosmology. For every answer we uncover, new questions multiply. We know that 95% of the universe is made up of dark matter and dark energy, and yet we don't know what they are. We can describe their effects, measure their influence, and simulate their outcomes, but their true nature remains hidden. This tension between knowledge and mystery creates a tone unlike any other field of study. Not frustration, but anticipation. It's as if the universe is a grand novel, and we've just begun to read the first few pages. We know that there's a plot, that the characters are developing, that the themes are emerging, but the ending, and even the middle chapters, are still waiting to be discovered. That's the tone that drives cosmology. Not certainty, but curiosity. Not closure, but exploration. And it's not just scientists who are moved by this atmosphere. Writers, filmmakers, artists, and musicians have all been drawn to the cosmic setting. The stars have inspired symphonies and screenplays, poetry, and paintings. There's a reason the genre of science fiction thrives in the cultural imagination. It channels the atmosphere of the cosmos into human stories. It lets us project our hopes and fears, our philosophies and dreams, onto a stage so grand that anything feels possible. The atmosphere of space isn't cold and empty, it's electric with possibility. It is a setting where time can stretch and bend, where reality itself can shimmer with unrevealed truths. It is a setting that invites every kind of imagination, from the scientific to the spiritual. So as you picture the universe, not just as data or diagrams, but as a living, dynamic, evolving whole, feel the atmosphere it creates around you. Feel the vastness, not as distance, but as invitation. Feel the galaxies as more than star systems, as cities of fire and memory. Feel the voids as more than absences, pauses in a cosmic symphony. Feel the dark matter not as an obstacle, but as a secret waiting to be told. This is the cosmos we inhabit. This is the story we're part of. And it is still being written, still being explored, still being felt. The atmosphere is thick with questions. The air of the universe is made of wonder, and we, small and temporary as we are, have the tools to breathe it in. There's a quiet tension that runs through the heart of cosmology, a sense that the more we know, the more elusive the truth becomes. It begins subtly, almost imperceptibly, as if hidden between the lines of scientific papers and embedded in the edges of satellite images. But the deeper we dive into the nature of the universe, the more we encounter paradoxes, uncertainties, and questions that resist resolution. These aren't minor obstacles that time and technology will simply erase. They are fundamental challenges to our understanding of space, time, and the nature of reality itself. And in this rising fog of ambiguity lies a quiet but profound conflict. What if the ultimate truth about the universe, the edge, the totality, the final theories, something we are forever doomed to chase but never grasp? What if the universe has built-in blind spots, horizons not just of sight but of knowledge? What if the very tools we rely on, logic, math, instruments, theory, are themselves part of the limitation? The first signs of this conflict emerged long before we had the language of cosmology. Philosophers like Zeno puzzled over paradoxes of motion and space, sensing that reality might be more slippery than our senses suggest. But it wasn't until the early 20th century that the clash between observation and theory began to take shape. Einstein's theory of general relativity described gravity as the warping of space-time and predicted phenomena like black holes and gravitational wavesum, of which took nearly a century to confirm. Yet, as powerful as relativity was, it didn't play well with quantum mechanics, the framework that governs the very small. In relativity, space-time is smooth and continuous. In quantum mechanics, it's probabilistic, discrete, and chaotic. When scientists tried to unite the two into a quantum gravity theory, something that could describe what happens inside a black hole or at the Big Bang, they found contradictions. The mathematics breaks down. Infinities appear. Reality, under the microscope, seems to resist being fully resolved. These paradoxes are not just theoretical curiosities. They strike at the heart of our efforts to find a theory of everything. Consider the black hole information paradox. According to quantum theory, information can't be destroyed. But according to classical interpretations of black holes, anything that falls into one disappears forever. Hawking radiation, other prediction of quantum theory, suggests that black holes evaporate over time, but it's still debated whether the information they consume can ever be retrieved. Is it encoded in the radiation? Lost in a baby universe? Or is something fundamentally flawed in the way we think about space and time? These questions create a fracture in our model of the universe, a hint that our best theories are incomplete. And yet, these very paradoxes point to deeper truths, as if the universe is whispering, "You're close, but not quite there." Then there's the cosmic horizon, the edge of the observable universe. It's not a wall or a border, but a limit set by the speed of light and the age of the universe. We can only see objects whose light has had time to reach us since the Big Bang, about 13.8 billion years ago. Because the universe has been expanding, this radius extends to 46.5 billion light-years in every direction. But beyond that, we don't know. We can't know. Not with current tools, not with any foreseeable ones. It's not a matter of building a better telescope. It's a fundamental limitation of causality. Light from beyond that horizon hasn't had time to get here and never will. If cosmic expansion continues to accelerate due to dark energy, that means vast regions of the universe are permanently hidden from us. They could contain other galaxies, other physics, or be completely empty. But we will never see them, ever. That's not just inconvenient, it's a hard boundary built into the fabric of reality. And what lies beyond that observable sphere is not just a question of distance, it's a question of interpretation. If the universe is infinite, then the horizon is just a local illusion, like the curve of the Earth from a high mountain. There's more out there, but we can't reach it. If the universe is finite, it might curve back on itself, like the surface of a sphere, so that traveling far enough in one direction would bring you back to your starting point. But even if that's true, how would we ever know? Cosmic curvature is incredibly subtle. Measurements from the cosmic microwave background suggest the universe is flat to within a 0.4% margin of error. That might mean it's truly infinite or just very, very large. In either case, we are left with a question that refuses to yield an answer. And in that refusal lies the shadow of the conflict. Some truths may be undecidable, not just practically, but fundamentally. Quantum mechanics brings its own set of boundaries. The Heisenberg uncertainty principle tells us we can never know both the position and momentum of a particle with perfect accuracy. On its own, that sounds like a minor technicality, but its implications are profound. It means that determinism, the idea that knowing all the initial conditions allows you to predict the future, is broken. The universe, at its most fundamental level, is not a machine, but a probability cloud. This makes predictions inherently statistical, and when applied to the early universe, it suggests that certain aspects of our cosmos, like the specific distribution of galaxies or the strength of cosmic inflation, may be the result of quantum randomness. In other words, our universe might be just one realization among infinite possibilities, shaped not by necessity, but by chance. That randomness introduces an unsettling possibility that some of the features we observe aren't reflections of deep principles, but just cosmic luck. And if that's true, then some questions about why things are the way they are may have no answer, only because that's how it turned out here. The idea of a multiverse only amplifies this problem. In some versions of inflationary cosmology, the universe is constantly spawning new regions, bubble universes with their own properties, physics, and histories. Ours is just one among many. That may sound exciting, even hopeful, but it also renders some questions meaningless. If every possible outcome exists somewhere, then what can we say about our own universe that isn't just anthropic reasoning? We observe this because otherwise we wouldn't be here to observe it. That line of thought, while logically consistent, drains mystery of its explanatory power. It replaces the search for fundamental truths with a shrug. And for many scientists and philosophers, that's deeply unsatisfying. It's not a dead end, but it feels like one. Another brick wall we've run into while trying to map the infinite. Technological limits deepen the conflict. Our instruments, no matter how sophisticated, are bounded by the laws of physics. We can't build a telescope bigger than Earth or see through opaque eras of the early universe where light couldn't travel freely. We can't send probes beyond our galaxy, or even to the nearest star system, within any reasonable time frame. Our particle accelerators can't recreate the energies present during the earliest moments of the Big Bang. And every time we try to simulate the universe, we are limited by computing power, initial assumptions, and our still fragmented understanding of quantum gravity. These limitations are not trivial. They shape what we can test, what we can confirm, and therefore what we can know. Even the known unknowns, like dark energy, resist precise characterization, and the unknown unknowns, whatever lies beyond the standard model, remain hidden in shadow. Yet, despite all this, we keep going. And perhaps that is the real heart of the conflict. We are a species defined by curiosity, but we live in a universe that may never fully yield to our questions. Every discovery sharpens our insight, but also exposes deeper gaps. The tension between knowing and not knowing is not temporary, it is structural. It is the boundary condition of human existence. We evolved to see and understand a narrow band of reality: visible light, audible sound, social complexity. We were not built to grasp quantum foam, curved space, time, or 11 dimensions. And yet, we reach for them. We build machines to extend our senses. We invent mathematics to describe what we cannot see. We run simulations to mimic what we cannot visit. This refusal to settle is beautiful, but it also reminds us that we are limited not just by biology, but by logic itself. Some truths may forever elude us, not because we're not smart enough, but because they are beyond the reach of finite minds in a boundless cosmos. Even time itself may be a barrier. The farther we look into the universe, the further back in time we see. But there is a limit. The cosmic microwave background, the fog of photons released 380,000 years after the Big Bang. Before that, the universe was opaque. No light can come from earlier times. Only indirect clues, neutrinos, gravitational waves, or mathematical inference. And so, the birth of time, the exact instant of the Big Bang, remains hidden behind a veil we may never lift. We can edge closer, refine our models, build better detectors, but the absolute beginning may remain just out of reach, eternally suggested, never fully revealed. At the core of modern cosmology lies a growing tension, not just between ideas, but between the very foundations upon which those ideas are built. The more we peer into the cosmos, the clearer it becomes that we are navigating a landscape riddled with contradictions. Theories that elegantly describe small fragments of reality begin to splinter under the weight of universal application. Competing models of the universe battle for legitimacy, each grounded in compelling logic, yet often in opposition to one another. Some of the greatest minds in science find themselves at a standstill, unable to reconcile the smooth predictability of general relativity with the chaotic uncertainty of quantum mechanics. And all of this conflict, all of this scientific drama, revolves around one question that remains maddeningly unresolved. What is the true nature of the universe, and does it have an edge? The struggle begins with our models of the universe's structure. On one side, general relativity has proven itself to be a profoundly successful theory. From the bending of light around stars to the expansion of the universe itself, Einstein's equations have delivered stunningly accurate predictions. General relativity tells us that space is not a static stage on which matter dances. It is dynamic, curved, and shaped by the energy and mass it contains. But relativity operates best on large scales, when things are smooth, continuous, and predictable. On the other end of the spectrum lies quantum mechanics, the realm of uncertainty, probability, and strange behaviors. Here, particles can exist in multiple states at once, entangle across vast distances, and tunnel through barriers. This framework explains everything from the behavior of atoms to the mechanisms inside stars. But when cosmologists try to unite these two pillars, when they try to describe the moment of the Big Bang or the heart of a black hole, everything collapses. Singularities emerge. Infinities appear in the math. Theoretical models break down, not from lack of imagination, but because the laws themselves refuse to cooperate. This fundamental discord has led to a theoretical arms race. Some physicists propose string theory of Bold, mathematical framework in which particles are actually tiny vibrating strings, and the universe has more dimensions than we can perceive. Others suggest loop quantum gravity, which attempts to quantize space-time itself, replacing smooth geometry with a network of discrete loops. Both camps are racing to explain how gravity works at quantum scales and to describe what happened at the universe's beginning. But despite decades of work, no theory has emerged as definitive. There are no decisive experiments that validate one over the other. Worse yet, these theories make predictions about scales and energies far beyond what any particle collider or telescope can currently observe. The result is a growing divide between mathematical elegance and empirical verification, a rift that leaves cosmologists drifting between possibility and proof. Nowhere is this tension more visible than in the debate over whether the universe is finite or infinite. On one hand, observations suggest that the geometry of the universe is flat, meaning that, on the largest scales, it neither curves inward like a sphere nor outward like a saddle. A flat universe implies that space could extend forever, with no edge, no boundary, no final frontier. This matches well with the inflationary model of the universe, which suggests that in the first fraction of a second after the Big Bang, the universe expanded faster than the speed of light, smoothing out any curvature. But there is a counterpoint. A universe can be both flat and finite-like, the surface of a video game screen that wraps back on itself. You could travel in one direction indefinitely and eventually return to where you started. In that model, the universe has no edge in the traditional sense, but it does have a topologia shape that repeats. The problem is, both models can fit the same observational data. The cosmic microwave background doesn't tell us whether the universe is truly infinite or just very, very large. The temperature fluctuations we observe are consistent with either possibility. So again, theory collides with measurement and no definitive answer emerges. This ambiguity leads to deeper philosophical and scientific tensions. If the universe is infinite, then every possible configuration of matter must exist, somewhere including exact copies of Earth, of you, of every moment you've ever experienced. This idea, supported by mathematical logic but lacking any observational support, raises profound questions about meaning, probability, and identity. But if the universe is finite, then we can, in theory, describe its total content, show much matter exists, how many stars there are, what its eventual fate will be. Yet both models face their own theoretical challenges. An infinite universe seems to break down when applied to thermodynamics. Do you define entropy in a space that never ends? A finite universe, meanwhile, must contend with boundary conditions. What happens at the edge? Does space fold? Does it stop? What exists outside it? Adding to the complexity is the issue of the cosmic horizon. We can only observe a finite portion of the universe, everything within the distance that light has had time to travel since the Big Bang. That radius defines the observable universe, a sphere about 46.5 billion light-years in every direction. But what lies beyond that horizon? More of the same? Different physics? A mirror universe? We don't know, and worse, we may never know. Cosmic expansion, driven by dark energy, is accelerating. The farther away a galaxy is, the faster it moves from us. Eventually, galaxies will disappear from our sky, redshifting beyond detectability, not because they cease to exist, but because the expanding space between us stretches their light to undetectable wavelengths. This creates a fundamental observational limit. There are regions of the universe we can never see or interact with. Even in principle, no experiment or probe can reach them. This is not a temporary barrier, it is a permanent wall in space-time, and it suggests that our understanding of the cosmos will always be partial. These conflicts ripple through every major question in cosmology. Take dark matter. We know it exists. Its gravitational influence is measurable in galaxy rotation curves, lensing events, and cosmic structure formation. But we don't know what it is. None of the particles in the standard model of physics fit the profile. For decades, scientists have searched for WIMPs, weakly interacting massive particles, axions, sterile neutrino-hypothetical particles that might explain dark matter. Yet no detector has found them. Every new null result deepens the conflict between theory and observation. Is our model of gravity wrong? Is dark matter not a particle at all? Or are we simply blind to its true nature? Likewise with dark energy, the enigmatic force driving the acceleration of the universe's expansion. It accounts for nearly 70% of the total energy in the cosmos, yet we have no idea what it actually is. Is it a property of space itself, like Einstein's cosmological constant? Or is it a dynamic field that evolves over time, like quintessence? Again, multiple theories exist, but no decisive evidence favors one over the other. The observable universe itself adds to the conflict. We can simulate the large-scale structure of the cosmos with incredible accuracy. We can trace the evolution of galaxies, model the growth of black holes, and even reproduce the temperature fluctuations of the early universe. But we still hit theoretical walls when we ask the deepest questions. What happened before the Big Bang? Did time exist? Was there a singularity, or was it a transition from a previous state? Some models suggest a bounce universe that contracts, reaches a minimum size, and expands again. Others invoke quantum fluctuations or eternal inflation, where our universe is just one bubble in a cosmic foam. But all of these are untested, perhaps untestable. And that's the heart of the conflict. The line between science and philosophy begins to blur. Cosmologists are deeply aware of this. The field is not plagued by ignorance, but haunted by the awareness that some answers may always remain just out of reach. Every new model brings hope and skepticism. Theories are judged not only by their explanatory power, but by their falsifiability, their testability. And as our instruments become more sensitive, our questions become more abstract. The farther we peer into space, the more we confront the limits of our own perception. We are creatures evolved for life on a small planet, using tools to uncover truths that may lie outside the scope of human comprehension. This isn't to say that progress is impossible. Quite the opposite. Cosmology continues to evolve rapidly. New missions like the James Webb Space Telescope, the Vera Rubin Observatory, and the Euclid satellite promise to gather data that could clarify these tensions or sharpen them. We may find new anomalies in the cosmic microwave background. We may detect the nature of dark matter. We may even find evidence of multiverse interactions or new physics. But each discovery may also bring more complexity, more questions, more debate. If the universe truly has no edge and no boundary, no outer limit, no final destination where space ends and something else begins, then we are living inside a reality that defies every ancient instinct we've carried as a species. Since the dawn of time, human beings have drawn maps, walked borders, defined horizons, and sought endings. Our minds are built to divide the known from the unknown, to believe that everything has a start and a finish, a place and a limit. But the idea of a boundless cosmos, one that stretches forever in all directions or loops back on itself endlessly, challenges not only the way we think about the universe, it challenges how we think about everything. What if there is no edge? Then there is no center, no privileged position, no destination, no grand perimeter to cross into the final answers. This forces physics to reconsider the very structure of the universe and forces philosophy to confront the terrifying possibility that our desire for completion may never be fulfilled. Physically, an edgeless universe removes any idea of an outside. There is no exterior perspective, no realm from which one might observe the totality of creation. We are always inside, always limited by what light can reach us. If space extends forever, then our observable universe, the sphere, roughly 93 billion light-years across, is just a tiny patch on an incomprehensibly vast cosmic quilt. This patch might appear representative of the whole, or it might be an anomaly. But if the rest is forever hidden from us, we may never know. Cosmology, then, becomes a science of local inference. We model the whole based on the part, and we assume hope that what we see is typical. But that assumption becomes fragile in the face of infinity. If space is infinite, and if inflation-created bubble universes scattered across that infinity, then there may be regions governed by entirely different laws of physics. Our physical constants, things like the strength of gravity or the mass of the electron, might be just one set among countless possibilities. And if that's true, then many of the why questions we ask could be answered with "because that's how it turned out here." This has enormous consequences for physics. The pursuit of a grand unified theory, a single elegant framework that explains all forces and particles, depends on the assumption that our universe is unique, that its laws are universal. But if we are just one universe in a multiverse, or one region in an infinite cosmos, then the laws we observe might be local rules, not global ones. That doesn't make them wrong, it makes them contextual. Like the rules of a particular game in a vast playground where other games are being played with different rules. That possibility forces physicists to rethink what a fundamental law really means. Is it something necessary and unchanging, written into the fabric of all reality? Or is it more like a habit of nature that holds true in our region but not beyond? The difference is profound. It shifts the goal of physics from finding ultimate truths to understanding environmental conditions. But if the universe has no edge, it doesn't just break physics, it destabilizes meaning. The psychological and philosophical consequences are vast. A finite universe gives a sense of narrative. It begins, it evolves, and perhaps one day, it ends. But an infinite, boundless cosmos has no beginning or end in the traditional sense. Even if the Big Bang marked the start of our observable universe, in an infinite cosmos, it may have been just one local Evanton flare-up in a timeless sea of possibility. That removes the notion of a cosmic timeline. There is no universal clock, no single now that binds the cosmos together. Every observer, everywhere, sees their own slice of time. And in that endless spread of space and time, questions of significance, identity, and destiny take on strange new shapes. What does it mean to be human in a universe without edge? For some, it inspires awe. It means we are part of something grand, something unending, something whose scale is so vast that it silences all arrogance. Every life becomes both infinitesimal and precious, a fleeting moment of awareness in a sea of timeless expansion. But for others, the same idea provokes existential vertigo. If the universe has no boundary, then perhaps there is no larger purpose, no endpoint where meaning is revealed. The journey never ends. The map is never complete. The mystery is never solved. In such a cosmos, meaning cannot be imposed from the outside, it must be created from within. That demands a kind of spiritual courage, a willingness to live without final answers, to embrace uncertainty not as a flaw, but as a feature of being. This tension fuels a deeper need for new physics. The models we have, relativity, quantum mechanics, the standard model of particle physics have brought us astonishing insights, but they are incomplete. They break down at extremes, the singularity at the heart of a black hole, the moment of the Big Bang, the unexplained acceleration of the universe's expansion. These breakdowns are not minor glitches. They are signals that our frameworks are approximations. Something deeper waits beneath them, something more unified, more elegant, or perhaps more radical. Maybe we need a theory that merges space-time and quantum fields into a single entity. Maybe we need to abandon the idea of space and time altogether and reconstruct reality from information, energy, or even consciousness. The truth is, we don't yet know what theory of everything even looks like. But the absence of an edge in the universe is a clue. It suggests that our current tools may be insufficient, not just technologically, but conceptually. One promising avenue is the idea of holography, notion that the universe we experience in 3 dimensions might be encoded on a 2-dimensional boundary we cannot perceive. This idea, drawn from string theory and supported by black hole thermodynamics, flips our intuition. In such a framework, space and gravity are emergent properties, not fundamental ones. That could explain why we can't find the edge of the universe, because it isn't out there in space. It's encoded in the informational structure of the universe itself. If such ideas prove true, they could redefine not only cosmology, but our understanding of reality at every level. But these theories are still speculative, still mathematical, still awaiting experimental support. In the meantime, the absence of an edge imposes a unique kind of humility on science. It reminds us that we are working within constraints, that the universe is not obligated to be comprehensible, that some truths may lie forever beyond our event horizon. But it also reminds us of our extraordinary progress. A species born in the dirt of a single planet, orbiting a single star, has managed to construct models of reality that stretch across billions of light years and billions of years. We've measured the age of the universe, mapped the afterglow of its birth, discovered the invisible scaffolding of dark matter, and detected the faint tremors of colliding black holes. These are not small feats. They are the work of generations, of questions asked in the dark and answered with light. And even if we never find the edge, we have already crossed a more profound boundary, the boundary between ignorance and curiosity. The philosophical impact of an edgeless universe extends beyond science. It touches ethics, theology, even art. If the universe has no boundary, then there is no outside from which to judge its contents, no fixed standard, no divine viewpoint. That invites a radical freedom and a radical responsibility. We must choose what matters. We must define our own edges, our own centers, our own values. And in doing so, we turn the absence of an edge into a kind of invitation to grow, to explore, to imagine without limits. For many, this leads to a sense of unity. In a boundless cosmos, we are all equally small. National borders, cultural divisions, even species differences fade against the backdrop of cosmic scale. We are one world, one biosphere, one thread in the fabric of the infinite. That perspective can foster compassion, cooperation, and a shared sense of purpose. Or it can provoke fear, nihilism, and retreat. How we respond to the infinite is a reflection of who we are. It challenges us to expand not only our knowledge, but our wisdom, to build civilizations that respect the scale of what we are part of, and to live lives that honor the miracle of consciousness in a universe that owes us nothing. And so, the absence of an edge is not the end of the story, it is the beginning of one. It is the open horizon on which we project our best questions, our boldest theories, our deepest emotions. It is the silence into which we speak our truth, knowing that the echo may never return. But still, we speak. Still, we search. Still, we ask, what lies beyond what we can see? What lies beyond what we can know? And in asking, we become more than creatures of biology. We become participants in the great unfolding, witnesses to the infinite, and authors of a future still unwritten. The universe may have no edge, but we do. And the way we respond to that truth will shape everything that comes next. There comes a moment in every great story when the trajectory shifts, when the clues accumulate, the tension builds, and something changes forever. In the story of the universe, we are living in that moment. The turning point is not a single discovery or headline, but a convergence of insights, data, and technological triumphs that are transforming our view of the cosmos at a breathtaking pace. We have long suspected that the universe was more complex, more vast, and more mysterious than our senses suggest. But only in recent decades have we begun to grasp just how strange and how astonishing our cosmic reality truly is. The past few years have delivered a series of breakthroughs that have shifted the landscape of cosmology, forcing us to rewrite the narratives we thought were stable. And now, with new telescopes in orbit, new models in development, and new questions rising faster than we can answer them, we are standing on the threshold of a new cosmic era. One of the most significant turning points in modern cosmology was the discovery of the universe's accelerating expansion. Until the late 1990s, scientists believed that the expansion of the universe, initiated by the Big Bang, was gradually slowing down due to the gravitational pull of all the matter it contained. That expectation seemed reasonable after all. Gravity pulls things together. But in 1998, two independent teams studying distant Type Ia supernovae exploding stars, used as cosmic mile markers, found something shocking. The supernovae appeared dimmer than expected, suggesting they were farther away than they should be. The conclusion was inescapable. The expansion of the universe wasn't slowing down, it was speeding up. This revelation rewrote everything. It implied that some unknown force was pushing space apart, working against gravity and overwhelming it on cosmic scales. That force was named dark energy, and it instantly became one of the biggest puzzles in physics. The role of dark energy in shaping the universe cannot be overstated. It affects everything from the future fate of the cosmos to our ability to observe its distant parts. Unlike matter, which clusters and slows expansion through gravity, dark energy seems to have a repulsive effect. The more space there is, the more dark energy there is, causing a feedback loop that accelerates the expansion over time. Today, dark energy is believed to make up about 68% of the total energy content of the universe, with dark matter at 27% and ordinary matter, everything we see, touch, and know, making up a mere 5%. This shocking ratio suggests that the vast majority of the cosmos is composed of substances and forces we do not yet understand. It also means that our observable universe is shrinking in terms of what we will eventually be able to study. As the expansion accelerates, distant galaxies are being pushed beyond our cosmological horizon, making them forever inaccessible. In time, even the light from currently visible galaxies will be stretched so far that it will no longer reach us. We are living in a golden window of cosmological discovery, a time when the echoes of the early universe still whisper to us, and when light from distant galaxies still arrives. But that window is closing. The expansion is speeding up, and with it, the curtain is slowly falling on the deepest acts of cosmic history. This cosmic shift has inspired a technological renaissance. If we are to understand the nature of dark energy, dark matter, and the birth of the universe, we must build tools capable of peering farther, measuring more precisely, and modeling more completely than ever before. And we have. The James Webb Space Telescope, JWST, launched in 2021, is one of the most ambitious instruments ever constructed. With its infrared capabilities, JWST can see through clouds of gas and dust to witness the birth of stars and galaxies billions of years ago. It is capable of detecting the faint light from the earliest galaxies, formed just a few 100 million years after the Big Bang. Already, its images have revealed galaxies that seem more mature than expected, challenging assumptions about how quickly structure formed in the early universe. Some of these galaxies appear massive and well-organized far earlier than standard models predicted, suggesting that our understanding of cosmic evolution may be incomplete. These are not just beautiful pictures. They are cracks in our current theories and clues to something deeper. Alongside JWST, the upcoming Vera-C Rubin Observatory will conduct a 10-year legacy survey of space and time, LSST, capturing the entire southern sky every few nights and generating a dynamic map of the universe in motion. This unprecedented data stream will allow scientists to track changes in dark energy over time, study the motion of galaxies and clusters, and probe the large-scale structure of the cosmos. The Euclid mission, launched by the European Space Agency, is similarly focused on unraveling the mysteries of dark energy and dark matter by measuring the shapes and distributions of billions of galaxies. Together, these projects represent a new phase in cosmology, defined not just by observation, but by statistical power, deep learning, and simulation. We are no longer just looking at the universe. We are quantifying it on scales never before imagined. But the technological turning point isn't limited to telescopes. Gravitational wave astronomy, pioneered by the LIGO and Virgo collaborations, has opened an entirely new window into the cosmos. By detecting the ripples in space-time caused by massive objects like merging black holes and neutron stars, we are now listening to the universe as well as seeing it. These detections have confirmed predictions made a century ago by Einstein, but more importantly, they have inaugurated a new era of multi-messenger astronomy where light, gravitational waves, neutrinos, and cosmic rays all provide complementary views of cosmic events. This integrated approach is already yielding surprises. For example, the merger of two neutron stars observed in both light and gravitational waves provided crucial insights into the origin of heavy elements like gold and platinum, and offered a new method to measure the expansion rate of the universe, the Hubble constant. And here lies another critical turning point: the growing tension between different measurements of the Hubble constant. When we use observations of the cosmic microwave background from the early universe, as measured by the Planck satellite, we get one value for the rate of expansion. But when we use measurements based on local observations, like supernovae and Cepheid variable stars, we get a significantly higher value. This discrepancy has persisted despite increasingly precise measurements, and no systematic error has yet been found to explain it. Some scientists believe it may point to new physics, perhaps a change in the behavior of dark energy, or the presence of unknown particles in the early universe. Whatever the cause, the Hubble tension is a symptom of a deeper transformation. We are reaching the limits of our current models, and the universe is beginning to resist easy explanation. This is what makes the current era such a profound turning point. We are armed with better data, sharper theories, and more powerful tools than ever before. And yet we are discovering that the universe is more complex, more dynamic, and more surprising than we imagined. The pieces no longer fit together perfectly. The standard model of cosmology, while still incredibly successful, is showing strain. The cosmic puzzles we face: dark matter, dark energy, inflation. The nature of time and space are not footnotes to be tidied up later. They are central mysteries. They are signposts pointing us toward a deeper layer of reality. And the fact that we can even perceive these mysteries is a triumph of the scientific spirit. We are no longer asking whether the universe is expanding. We are asking why it accelerates, what drives its geometry, and whether it had a beginning at all. We are not just studying stars and galaxies. We are exploring the very fabric of existence, the way space and time emerge, the boundary conditions of the cosmos, and the possibility of other universes beyond our own. These are questions that blur the line between physics and philosophy, between science and something more ancient and emotional, the human longing to understand where we come from and what we are a part of. Every major revelation of the last few decades, from the detection of dark energy to the confirmation of gravitational wave shafts, pushed us closer to that understanding, even as it has complicated the path. And each new instrument, each new theory, each new anomaly becomes a part of the turning point. We are no longer gathering facts to complete a known picture. We are discovering that the picture itself is larger, stranger, and more alive than we ever imagined. We are not reaching the end of cosmology. We are standing at its beginning. The turning point is not a crisis, it is an awakening, an invitation to think bigger, to imagine wider, to be humble in the face of the infinite. It is a reminder that the universe is not a solved puzzle, but a living mystery, still unfolding, still speaking, still waiting to be heard. And we are here, in this moment, with eyes on the sky, instruments in hand, questions on our lips, and wonder in our hearts. We are the generation that turned the page. We are the explorers who found the edge and realized it was only the beginning. What if everything we think we know about the universe, its size, its shape, its very substance, is only a shadow of something deeper, something radically different from how it appears? What if we're not just missing a few pieces of the cosmic puzzle, but are staring at the wrong puzzle altogether? For centuries, science has advanced by building on the assumption that space and time are the stage on which the universe plays out. Matter and energy move through this space, and time ticks forward relentlessly. But a growing body of evidence, theoretical tension, and philosophical insight suggests that we may be approaching the problem from the wrong angle. As our instruments grow more sensitive and our equations more complex, a subtle but powerful shift is taking place. The understanding that space and time themselves may not be fundamental. They may not be the bedrock of reality. Instead, they may emerge from something deeper, something stranger. This shift in perspective is not just a change in scientific vocabulary. It is a revolution in thought, a turning inward, a questioning of the very foundations of our reality. One of the most provocative ideas born from this shift is the holographic principle, idea that everything we observe in 3 dimensions, including space, time, and gravity, may actually be a projection of information stored on a 2-dimensional boundary. It sounds like science fiction, but it's rooted in the very real physics of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes possess entropion intrinsic amount of information proportional not to their volume but to their surface area. That's odd. In most systems, the amount of information scales with volume, but black holes suggest that all the information that falls into them is encoded on their surface, like a cosmic memory etched onto the event horizon. This led physicists like Gerard Hooft and Leonard Susskind to propose that the universe itself may work the same way. Everything inside a galaxy, a planet, your thoughts might, be the result of quantum data projected from a faraway boundary we cannot perceive. The holographic principle is more than a mathematical trick. It represents a shift in how we think about reality. It suggests that space is not a pre-existing container, but an emergent property result of quantum entanglement, information, and thermodynamic laws at work. It means that gravity itself, which we've always viewed as a fundamental force, might actually arise from the statistical behavior of microscopic degrees of freedom. If that's true, then what we think of as the universe is more like a simulation than a sandbox, not in the digital sense, but in the sense that its dimensions and interactions are derived from something non-spatial and more fundamental. This idea resonates with another radical shift: the increasing belief that quantum mechanics, not general relativity, may be the true foundation of cosmic structure. General relativity is a beautiful deterministic theory that describes the large-scale curvature of space-time, but it breaks down at the smallest scales, and in the most extreme conditions, black holes, the Big Bang, where quantum mechanics takes over. Quantum mechanics, by contrast, is not deterministic. It is probabilistic, governed by wave functions, superposition, and uncertainty. For a long time, these two frameworks seemed irreconcilable, but recent efforts in quantum gravity, string theory, and loop quantum gravity suggest that space-time itself may be woven from the threads of quantum information. If space-time emerges from quantum entanglement, then our classical notion of space as something absolute collapses. What we perceive as here and there may not be objectively distant. The distance between two regions in space may be determined not by physical length, but by how entangled they are. The more entangled, the closer they are in the fundamental structure of reality, even if they appear distant in classical space. That's a stunning shift in viewpoint. It redefines what it means to be connected. It suggests that the fabric of the cosmos is not made of particles or strings, but of relationships, correlations, in a vast network of quantum information. This view aligns with research in AD-S CFT duality, a mathematical realization of the holographic principle, where a universe with gravity is dual to a lower dimensional theory without gravity. These conceptual breakthroughs are more than just abstract philosophy. They're beginning to shape scientific practice. Theoretical physicists are reimagining black holes not as singularities hidden by event horizons, but as complex quantum systems with entangled interiors and exteriors. Space-time itself is being modeled as a tensor network, a web of quantum information whose structure gives rise to dimensions, geometry, and gravity. New frameworks like emergent gravity and quantum gravity suggest that the familiar world is a low-energy, large-scale illusion that smooths out the messy quantum roots underneath. Even the Big Bang is being rethought. Some propose that it wasn't a beginning at all, but a phase transition, a change in the structure of information that gave rise to space-time as we know it. In these models, time itself is emergent. It isn't a fundamental arrow, but a statistical effect of increasing entropy or decoherence. This changing viewpoint reshapes scientific discussions across disciplines. In cosmology, it encourages models that go beyond the observable universe, incorporating hidden variables and non-local phenomena. In quantum computing, it inspires algorithms that simulate aspects of quantum gravity and holographic space. In philosophy of science, it revives debates about realism, causality, and the nature of knowledge. What is real, if reality depends on observation? What is cause, if entanglement can correlate events faster than light? And what does it mean to explain something if the explanations themselves emerge from the same statistical rules as the events they describe? Crucially, this shift demands a new language. Classical concepts like location, mass, energy, and even event may not be adequate. We are moving toward a physics of information where entropy, coherence, and entanglement are the true actors on the cosmic stage. This reframing doesn't discard the past, it builds on it. Just as Einstein's relativity extended Newtonian mechanics rather than erasing it, the emerging quantum cosmologies aim to extend our current models into a deeper, more unified picture. But they challenge us to let go of intuition, to abandon the comforting metaphors of space as a container and time as a river. Instead, we must embrace the strange idea that the universe is a computation, a geometry of thought, a system of relations that only appears solid when viewed from within. This change in perspective also affects how we think about the unknown. The concept of the edge of the universe, long a holy grail in cosmology, may be a Mirasian artifact of classical thinking. If space is emergent, then asking where it ends is like asking where the edge of a rainbow is. It's a meaningful question from a certain point of view, but ultimately, it dissolves when you understand the underlying mechanisms. Likewise, the boundary of the observable universe is not an edge in space, it's an edge in information, a limit to what we can decode, not what exists. And as such, it invites a shift in focus from mapping space to understanding entanglement, from measuring distances to decoding structure. Even consciousness finds a role in this framework. Some physicists and philosophers speculate that consciousness may not be a passive byproduct of matter, but an active participant in the emergence of reality. In interpretations of quantum mechanics like cubism or the participatory universe of John Wheeler, observers play a central role in defining outcomes. This is controversial and often misunderstood, but it reflects a broader idea that reality, at its deepest level, is not a set of objects in a container. It is a process of interaction, a web of feedback, a conversation, and we, as observers, are part of that conversation not just as listeners, but as speakers, as co-authors. This doesn't mean science becomes mystical. It means science becomes broader, more inclusive of new ideas and metaphors. The shift in perspective is not away from rigor, but toward a deeper kind of rigorone that includes complexity, uncertainty, and emergence. It asks us to replace the dream of complete control with the practice of continual questioning. It teaches us that knowledge is not the end of wonder, but its beginning. As this new viewpoint gains traction, it promises to reshape the next generation of scientific discovery. We will build quantum computers that model the universe not as space, but as information. We will design experiments to test whether gravity is emergent and whether space-time has a discrete, pixel-like structure at the Planck scale. We will explore whether the patterns we observe in the cosmic microwave background are encoded by deeper rules of computation. And we will face a new kind of humility, a recognition that the universe is not built for our understanding, but that understanding is built for our universe. Could we be looking at the problem the wrong way? Maybe. But the deeper truth is this: every major scientific advance in history has begun with that question. When Copernicus put the Sunday at the center, when Einstein bent time, when Bohr and Heisenberg embraced uncertainty, they weren't discarding knowledge, they were reframing it. And that's what we are doing now. Reframing our assumptions, rewriting the rules, reimagining the stage. It always happens the same way in the great narratives of science. The closer we come to thinking we figured it all out, the more the universe surprises us. A discovery comes along, subtle at first, then unmistakable. And it doesn't just alter a few equations, it calls into question the foundation itself. What if everything we assumed about space, time, and existence was wrong? What if our universe is just one of many? What if what we perceive as reality is in fact an illusion or a computation? These aren't fringe questions anymore. They are the subject of serious scientific papers, debated in prestigious journals, funded by powerful institutions. The unexpected twist in the story of the cosmos is that we are beginning to suspect the cosmos may not be ours, at all not unique, not ultimate, not even real in the way we once believed. And this twist doesn't lead to a conclusion. It opens a door into ideas so radical they force us to reimagine what it means to exist at all. One of the most destabilizing revelations in recent cosmology is the growing weight behind multiverse theories. What once seemed like science fiction is now a serious scientific proposal supported by mathematical models and indirect evidence. The idea has roots in the theory of cosmic inflation, the brief exponential expansion that occurred fractions of a second after the Big Bang. According to some versions of inflation, particularly eternal inflation, this process never truly ends. As our observable universe continues to expand, other regions of space continue inflating, creating bubble universes that pinch off and form their own isolated realities. Each bubble may have its own physical constants, laws, even dimensions. In some, gravity may be weaker, time may flow differently, or atoms as we know them may never form. If true, then our universe is just one small domain in a vast, unobservable multiversia cosmic archipelago scattered across an eternal ocean of possibility. This theory solves many problems. It explains the fine-tuning of the constants in our universe, why the forces of nature seem perfectly balanced to allow stars, planets, and life. In a multiverse with countless variations, some bubbles would naturally support life, and we simply find ourselves in one of those. This is known as the anthropic principle. The universe must be the way it is, because otherwise we wouldn't be here to observe it. But this explanation, while elegant to some, disturbs others. It shifts science from prediction to selection. It replaces fundamental laws with statistical accidents. And most unsettling of all, it makes our universe feel profoundly unexceptional. We are not at the center of creation. We are not even a guaranteed outcome. We are an accident of inflation and probabilitune of infinite variations. The implications go even deeper. If the multiverse is real, then there may be exact copies of you, living in other regions of space, making different choices. Every variation of your life could be playing out somewhere. In some universes, Earth never formed. In others, humanity is extinct. In still others, we may be thriving across the stars. This concept, often called the many worlds interpretation, is also echoed in quantum mechanics, where every quantum event spawns a branching set of realities. These ideas challenge the very notion of identity, destiny, and truth. If everything that can happen does happen, somewhere, what does it mean to choose? What does it mean to matter? Then, as if that weren't enough, comes a theory even stranger, the simulation hypothesis. Proposed most famously by philosopher Nick Bostrom, this idea suggests that if any civilization becomes advanced enough to create highly detailed simulations of conscious beings, and if they have an interest in doing so, then simulated realities could vastly outnumber base realities. Statistically, we are more likely to be in one of the simulations than in the original universe. This idea gained traction not just because of its logic, but because it resonates with emerging physics. Quantum mechanics often behaves in ways that mimic computation. Space-time may be discrete, like pixels. Black holes behave like information processors. And recent work on holography and entanglement suggests that the universe is structured like a complex data system. Elon Musk popularized the idea, but physicists like Seth Lloyd, Max Tegmark, and others have explored the idea seriously, that our reality may be underpinned not by matter, but by code. The simulation hypothesis doesn't mean we're living in a video game. It means that the fundamental substrate of the universe might be informational, not physical. It doesn't deny that we feel, think, and experience it challenges what those experiences are grounded in. And it reframes the search for physical laws as the search for rules in a program. If the simulation is real, can we find glitches? Can we detect the system's architecture? Can we ever exit or communicate with the creators? These questions border on metaphysical, but the fact that serious scientists are entertaining them is proof of how profoundly the unexpected twist has reshaped the scientific landscape. But these radical ideas don't exist in a vacuum. They're emerging in response to real tensions in the data. One of the most striking examples is the ongoing Hubble tension, the persistent discrepancy between the measured expansion rate of the universe from early universe observations, like the cosmic microwave background, late universe measurements, like supernovae. No matter how precisely the numbers are calculated, they don't agree. This conflict may be a sign that our standard cosmological model, known as WCDM, lambda cold dark matter, is incomplete. It could point to new physics unknown particles, shifting dark energy, or changes in fundamental constants. Or it could hint at something even bigger, that our entire framework for measuring cosmic time and distance is flawed. Another example comes from the James Webb Space Telescope, which has already spotted galaxies that appear too old and massive to fit within our current models of galaxy formation. These galaxies formed just a few 100 million years after the Big Bang, yet show signs of maturity and complexity that should not be possible so soon. This is more than an observational curiosity. It suggests that our understanding of how structure forms in the early universe may be wrong. Perhaps dark matter interacts differently than we thought. Perhaps inflation played out in a more complex way. Or perhaps, again, we are looking at a projection and emergent illusion that hides a more complex architecture beneath. These discoveries are not failures. They are revelations. They are reminders that the universe is not obligated to match our expectations. They invite humility, creativity, and above all, courage. Because every twist in the cosmic story asks us to let go of cherished ideas and embrace uncertainty. In doing so, we discover something not just about the cosmos, but about ourselves. And here, perhaps, lies the deepest realization of all. We are not central, and we never were. The Copernican principle told us we're not at the center of the solar system. Modern cosmology tells us we're not at the center of the galaxy or the universe. Multiverse theories tell us we may not even be at the center of reality. But in that decentralization, in that loss of cosmic specialness, we find a new kind of meaning. We are not central, but we are aware. We are not ultimate, but we are curious. We are not guaranteed, but we are here thinking, asking, building, wondering. If the universe is a simulation, then consciousness is the most powerful artifact within it. If the universe is one bubble among infinite others, then our very capacity to explore it is a miracle of emergence. If reality is a hologram, then our stories, our emotions, our questions, they are not less real. They are the way the pattern reveals itself. And that changes everything. We are not passive spectators in this cosmic play. We are participants. We are the universe folding back on itself in thought. When we ask, what is the universe? We are the universe asking itself. And the more radical the answer, the more sacred the question becomes. Science is not just a method, it is a kind of poetry, a language of the unknown spoken with equations and experiments, with telescopes and theories. And right now, that poetry is reaching new heights. It is writing stanzas we cannot yet interpret. It is pointing us toward a future we can only feel in hints and fragments. The unexpected twist is not an ending. It is an invitation to rethink, to reframe, to reimagine everything. It is a turning of the page in the greatest story ever told, the story of being, of awareness, of a small species on a pale blue dot, daring to ask questions of a universe it may never fully understand. But in asking, in reaching, in dreaming beyond the stars, we fulfill something greater than understanding. We fulfill the wonder that makes understanding worthwhile. And perhaps that is the true twist, that in a universe of infinite possibilities, the most unexpected outcome of all is us. Despite all the breathtaking progress cosmology has made, despite mapping the afterglow of the Big Bang, detecting gravitational waves, peering deeper into time than ever before, the truth is that we are still standing at the foot of a mountain whose summit we cannot yet see. For every mystery we've begun to unravel, new ones have emerged, more intricate and elusive than before. Each discovery sharpens the questions, deepens the paradoxes, and reveals the boundaries of our knowledge. These are not boundaries of imagination, but of instrumentation, computation, and theory itself. The story of the universe is not yet fully written, and for future scientists, the challenges ahead are as formidable as they are thrilling. We face the growing realization that our current tools, methods, and models may not be enough to answer the next generation of questions. The cosmos is speaking in signals that are too faint, too fast, too complex, or too far away for our present technology to decode. And so, the greatest task for 21st century cosmology is to invent new ways of listening, new eyes for seeing, and new languages for understanding. One of the most fundamental hurdles is the limitation of our observational reach. No matter how advanced our telescopes become, there is a hard limit to how far we can see the cosmic horizon, defined by the age of the universe and the speed of light. Light from beyond this horizon hasn't had time to reach us yet. And due to the accelerating expansion of space, it never will. This leaves vast regions of the universe forever inaccessible. Even within the observable universe, much of what we see is distorted by distance, motion, and the expansion of space itself. The farther away we look, the deeper into the past we peer, and the more we rely on inference rather than direct observation. Galaxies become redshifted and dim, their light stretched into infrared wavelengths that require highly specialized instruments to detect. We are limited not only by distance but by time. Most of the photons that carry information from the early universe are weakened by their journey, their signals drowned in cosmic background noise. Furthermore, there are epochs of the universe we cannot observe at all with current technology. The dark ages between the release of the cosmic microwave background, CMB, and the formation of the first stars are largely invisible to us. We know they happened, we can simulate them, but we have yet to directly detect signals from that era. Similarly, the Planck epoch, the first tiny fraction of a second after the Big Bang, when quantum gravity dominated, is completely beyond our reach. Light could not move freely then. The universe was opaque and chaotic, ruled by physics we do not yet understand. Even if we could build telescopes with perfect resolution, we still wouldn't be able to see past that veil. To explore these eras, we need new kinds of observables: gravitational waves, neutrinos, and possibly exotic particles that interact weakly with matter but carry information from the most ancient times. Another critical challenge lies in our incomplete understanding of dark matter and dark energy. These two components make up roughly 95% of the universe's total energy content, yet remain among the least understood. We know dark matter exists due to its gravitational influence on galaxies and large-scale structure, but we do not know what it is made of. It does not emit, absorb, or reflect light. It doesn't fit neatly into the standard model of particle physics. Countless experiments, like the Large Hadron Collider, Xenon, and Lux Zeppelin have tried to detect dark matter particles, but so far, they've come up empty. It's possible that dark matter is not a particle at all but a field, or an effect of modified gravity, or something even stranger that hasn't yet been theorized. The situation with dark energy is even more perplexing. It's a name we give to the observed acceleration of the universe's expansion, but we don't know its origin. Is it a cosmological constant? A dynamic field? A sign that we're misunderstanding the geometry of space? Or is it merely a placeholder for a deeper principle waiting to be uncovered? These questions cannot be answered with existing tools. We need next-generation space missions instruments that can push the frontier of precision and scale. The James Webb Space Telescope is a powerful step forward, but it is only the beginning. Missions like NASA's Nancy Grace Roman Space Telescope, set to launch in the coming years, aim to map dark energy with unprecedented detail by observing the shapes and distributions of galaxies across vast stretches of space. ESA's Euclid mission will complement this by exploring the geometry of the universe through weak gravitational lensing. The Square Kilometre Array, SKA, a massive radio telescope under construction in Australia and South Africa, will chart the evolution of hydrogen, the universe's most abundant element over cosmic time, offering insights into structure formation and the reionization era. These missions are not just bigger versions of older telescopes. They are designed from the ground up to tackle the deep mysteries of the universe. What is dark energy? How does dark matter behave over time? How did the first galaxies form? Is the expansion of the universe changing? Beyond telescopes, we also need more sensitive gravitational wave detectors, like the proposed LISA mission, Laser Interferometer Space Antenna, which will operate in space and be capable of detecting low-frequency gravitational waves that are currently invisible to Earth-based instruments. These waves could carry information from the early universe or from massive black hole mergers billions of light-years away. LISA will extend our hearing across the universe, potentially picking up signals from events that occurred before the universe became transparent to light. Additionally, experiments like IceCube and DUNE are studying neutrinos, ghostly particles that rarely interact with matter but can traverse the universe almost undisturbed, potentially providing a new channel of communication with the early cosmos. But even as we plan new missions, we must confront the computational challenges of modern cosmology. The amount of data generated by next-gen telescopes will be staggering petabytes of information that must be processed, analyzed, and interpreted. We are entering the era of big data astronomy, where human intuition alone is not enough. Artificial intelligence and machine learning will be essential to sift through the noise, identify patterns, and extract meaningful results. This will require not just better algorithms, but new theoretical models that can make sense of what we find. Current simulations of the universe, like Illustris and Eagle, are powerful, but still limited by assumptions about physics, resolution, and scale. To model the entire observable universe with full quantum detail is beyond our current computing power. And yet, that is where the answers lie. Scientists are aware of these hurdles and are already developing strategies to overcome them. Multidisciplinary collaboration is key, bringing together physicists, engineers, data scientists, mathematicians, and philosophers to ask better questions and build better tools. There is also a growing recognition of the need for global cooperation. The universe belongs to no one country or continent. Its secrets are a shared legacy of all humanity. Projects like the SKA, the Rubin Observatory, and the Event Horizon Telescope are being built through international partnerships, pooling resources, expertise, and creativity. Another approach is to redefine what counts as observation. We may never directly see the Big Bang or the multiverse, but we can detect their fingerprint subtle anomalies in the cosmic microwave background, unexplained correlations in the large-scale structure, deviations in gravitational wave spectra. In this way, cosmology becomes not a direct study of phenomena, but a science of consequences, a forensic analysis of cosmic history. By studying what we can see, we infer what we cannot. This requires new models of inference, new statistical tools, and a willingness to question long-held assumptions. Finally, we must confront the philosophical challenge of knowing what is knowable. As we press against the boundaries of observation and theory, we must ask, are there things about the universe that are forever beyond our reach? If so, how do we handle that? Do we accept it as a limit, or do we find new ways of asking? The future of cosmology is not just technical, it is conceptual. It asks us to consider frameworks like emergent space-time, the holographic principle, and quantum gravity, not as curiosities, but as starting points. It asks us to imagine that space, time, and matter are not what they seem, and that the next great leap will require not just new machines, but new minds. In the end, the hurdles that remain are not signs of failure. They are signs of health. They are the marks of a science that is alive, dynamic, and courageous. We don't know what dark energy is. We don't know if the universe is infinite. We don't know if we are alone. And that is what makes this moment so exhilarating. The frontier is wide open. The map is still being drawn. The mysteries are not diminishing. They are growing deeper, sharper, more beautiful. The story of the universe has always been one of tension between the known and the unknown, the measurable and the mysterious. But as we arrive at the current moment in our cosmic journey, it feels as though we are approaching a final confrontation, not a war in the traditional sense, but a reckoning between competing ideas, a collision of theories, and a fierce debate about what lies at the heart of everything. This confrontation is not a sign of failure, but a sign that science is alive, vibrant, and pressing against the outer limits of its understanding. At the center of this intellectual battlefield are some of the most powerful theories ever developed, each aiming to explain the deepest truths about reality, each with its strengths, weaknesses, and assumptions. But all of them are circling the same ultimate question: will we ever discover the true boundary of the universe, if such a thing even exists? And if we can't, can we at least unify our understanding of the universe into a single coherent theory that accounts for both the very large and the very small? The first contender in this confrontation is the well-established LCDM model, the Standard Model of Cosmology. It incorporates general relativity, the cosmological constant, lambda, associated with dark energy, and cold dark matter, CDM, and it has successfully explained a vast range of observational data, the expansion of the universe, the cosmic microwave background, large-scale structure formation, and more. Its strength lies in its simplicity and its predictive power, but it has limitations. It cannot explain the nature of dark energy or dark matter, It does not resolve the Hubble tension, the discrepancy between different methods of measuring the universe's expansion rate. And it does not incorporate quantum mechanics. It is a model built on general relativity, and as such, it fails at the Planck scale, where quantum effects dominate. Opposing the classical elegance of general relativity is the chaotic beauty of quantum mechanics. Quantum field theory has allowed us to understand the behavior of particles, the fundamental forces, except gravity, and the structure of atoms. It is the basis for the standard model of particle physics, which has been confirmed by thousands of experiments, including those at the Large Hadron Collider. But the standard model is incomplete. It doesn't include gravity. It doesn't account for dark matter. It cannot explain why the values of fundamental constants are what they are. And so, the confrontation becomes clear. Relativity describes the large-scale structure of space-time, and quantum mechanics describes the microscopic world of particles and fields, but the two refuse to merge. Bridging this divide has become the central quest of modern theoretical physics. Several competing frameworks have emerged, each vying to become the long-sought theory of everything. Among the most prominent is string theory, which posits that all particles are actually tiny vibrating strings existing in a multidimensional space, time usually 10 or 11 dimensions. String theory has the potential to unite gravity and quantum mechanics, and suggests that different vibrational modes of strings produce different particles. It even offers a natural place for the holographic principle via the ADS-CFT correspondence, which relates a gravity theory in a higher dimensional space to a quantum field theory on its lower dimensional boundary. This is a profound and beautiful idea, but string theory's greatest strength is also its greatest weakness. It has not yet made a testable prediction. It offers a vast landscape of possible solutions in the order of 10 circumflex 500 different possible universes, each with its own laws of physics. That makes it extremely flexible, but also difficult to falsify. In contrast to string theory, loop quantum gravity, LQG, takes a different path. Instead of unifying all forces, it focuses on quantizing spacetime itself. In LQG, space is not smooth and continuous, but made up of tiny loops woven into a fabric of finite Unitza granular geometry at the Planck scale. It suggests that space and time emerge from quantum processes, and that black hole singularities and the Big Bang may be resolved into non-singular quantum states. LQG has had success modeling early universe conditions and black hole entropy, but like string theory, it has yet to yield clear experimental tests. It is elegant, mathematically consistent, and deeply connected to the structure of general relativity, but it remains incomplete in unifying the other fundamental forces. And then there are emergent gravity theories, which turn the problem inside out. Instead of treating gravity as fundamental, they propose that it is an emergent phenomenon, something that arises from more basic ingredients like thermodynamics or quantum information. In these theories, space and time are not fundamental, they emerge from entanglement or quantum entropy. These ideas are radical, but they are gaining traction. They offer a possible explanation for the holographic nature of black holes, the thermodynamics of spacetime, and even the apparent weakness of gravity compared to other forces. But they also pose new questions. If gravity and space are emergent, what is the underlying structure that gives rise to them? How do we describe it? How do we test it? Amid these competing theories, a deeper philosophical debate is unfolding. Will we ever find a true edge to the universe? Some cosmologists argue that the notion of an edge is meaningless, that the universe is either infinite or finite, but unbounded, like the surface of a sphere. Others believe that the observable universe is just a small patch of a larger, perhaps fractal or foamy structure that continues forever, or loops back on itself in a higher dimensional topology. Still others suggest that what we call the universe is just one region of a multiverse, possibly with different laws of physics or even different dimensions. Each of these ideas carries profound implications. If the universe is infinite, then every possible configuration of matter, including exact duplicates of you, is realized somewhere. If it is finite but unbounded, then it has no edge, only a closed topology. If it is part of a multiverse, then our cosmic laws are just local rules and accident of initial conditions. But here lies the central problem. How do we test any of these ideas? The final confrontation may not come from theory alone. It may depend on our ability to extract new better data from the cosmos itself. That means pushing technology to new frontiers, more powerful telescopes, more sensitive detectors, and new kinds of observables. Projects like the Nancy Grace Roman Space Telescope, Euclid, and the Vera C. Rubin Observatory will provide vast datasets to map the structure of dark energy and dark matter. The Laser Interferometer Space Antenna, LISA, will open a new window on low-frequency gravitational waves, perhaps even detecting signals from the early universe. Next-generation particle accelerators may uncover evidence of supersymmetry, dark matter particles, or signs of extra dimensions. And emerging tools like quantum sensors, axion detectors, and neutrino observatories may detect new physics that lies beyond the standard model. Yet data alone is not enough. We also need new frameworks to interpret that data. That's why cosmology is increasingly interdisciplinary, drawing from quantum information theory, condensed matter physics, machine learning, and philosophy. New models may emerge from connections we haven't yet imagined, patterns in entanglement entropy, relationships between black hole thermodynamics and quantum computing, or new insights into the nature of time itself. We are moving into a realm where theory and computation merge, where simulations help build hypotheses, and hypotheses drive new computational models. The boundaries between disciplines are dissolving, just as the boundaries of space and time themselves may be more fluid than we once thought. This confrontation is not just scientific, it is existential. As we seek to unify the cosmos in our minds, we are also confronting the limitations of human understanding. Can finite beings ever fully grasp an infinite universe? Can we ever truly see beyond the observable horizon? Will we ever know what came before the Big Bang, if before even means anything? These questions are not distractions. They are the fuel of discovery. They remind us that cosmology is not just about equations in telescope PESIT, it is about who we are and what we are capable of becoming. The future of cosmology, then, is not a final answer, but a continuing evolution. It will be shaped by the interplay between competing theories, between the elegance of string theory, the pragmatism of quantum field theory, the insights of emergent gravity, and the constraints of observable data. It will depend on breakthroughs we cannot yet predict, new mathematical tools, unexpected anomalies in the data, or perhaps a unifying insight that brings together the best of all worlds. It will be driven by new generations of thinker-scientists who grow up not fearing the confrontation, but embracing it. And perhaps, in the end, the confrontation will not be resolved by choosing one theory over another, but by realizing that all our models are approximations, that reality is deeper, stranger, and more subtle than any framework we can create. The quest to unify relativity and quantum mechanics may not end in a single theory, but in a new way of thinking, paradigm shift that allows us to see connections where before we saw contradictions. In that shift, we may find not a boundary, but a bridge. At the heart of every great human endeavor, whether it be art, love, discovery, or science, there lies a single, persistent spark: curiosity. It is the engine that drives us to look beyond the horizon, to question what we see, and to challenge what we think we know. In the case of cosmology, that curiosity stretches to the furthest reaches of space and time, confronting the most profound questions we can ask. Where did we come from? What is the universe made of? Is there a boundary to existence? Are we alone? And, perhaps most haunting of all, why does anything exist at all? These questions are not only scientific, they are deeply human. They stir something primal in us, something sacred. And as we pursue their answers, we learn more than facts and equations. We learn about the very nature of our existence, our values, our hopes, and our future. That is the moral takeaway of cosmic exploration, that in seeking to understand the universe, we come to understand ourselves. The story of cosmology is a story of radical humility. Every step forward has dismantled a comfortable illusion. First, we learned that the Earth is not the center of the universe. Then, we discovered that our Sun is just one of billions in the galaxy. Then, that our galaxy is one of hundreds of billions in an expanding universe. And now, we face the possibility that our universe may be just one of an infinite number of universes in a multiverse too vast to comprehend. With each revelation, we are reminded of our smallness, and yet in that smallness, there is something transcendent. For we are not only part of the universe, we are a way for the universe to know itself. Through our curiosity, the universe becomes aware of its own structure. Through our science, the cosmos begins to understand its own laws. We are, as Carl Sagan once said, star stuff, contemplating the stars. This realization brings a profound moral clarity. It reminds us that the pursuit of knowledge is not about domination or control, it is about connection. When we gaze into the night sky, we are not conquering space, we are returning home. Every photon that enters our telescope carries a story from the past, a message from a distant star, a whisper from the early universe. These messages speak not just of chemistry and gravity, but of beauty, complexity, and the miracle of existence. They teach us that the universe is not a cold, indifferent void, but a place of structure, rhythm, and emergence. From the simplest particles arise galaxies, planets, and life. From randomness arises order, from nothingness, something, and from questions, meaning. Cosmic exploration teaches us that mystery is not the enemy of knowledge, it is its companion. Without mystery, there is no curiosity. Without the unknown, there is no reason to look further. Science thrives not by erasing mystery, but by dancing with it, refining it, reframing it, transforming it into deeper, more elegant forms. Each time we solve a puzzle, new questions arise. Each time we measure a phenomenon, we uncover an anomaly. This is not a failure, it is the essence of the scientific journey. The more we learn, the more we realize how much we have yet to learn. And this awareness fosters something rare in modern life, a sense of wonder. Wonder is more than awe. It is a moral stance. It is the ability to look at the universe and say, I do not understand, but I want to. I am not complete, but I am growing. I am not central, but I am part of the whole. This attitude fosters empathy, humility, and patience, qualities desperately needed in a world too often driven by ego, certainty, and division. Cosmic exploration reminds us that we share a single planet, orbiting a single star, in a single galaxy, among billions. Our differences of nation, race, belief fade when seen from space. The Earth becomes a fragile blue dot, suspended in darkness, and we are revealed not as enemies, but as fellow travelers on a common journey. The perspective of the cosmos is the perspective of peace. But the moral power of cosmic discovery does not end with unity, it extends to responsibility. The more we understand about the rarity and fragility of life, the more we realize how precious our world truly is. We now know that Earth is a rare oasis in a vast desert, that liquid water, stable climates, complex ecosystems, and intelligent life are astonishingly unlikely. The universe may be full of planets, but life as we know it may be vanishingly rare. If we are a loner, even if we are not, then our actions matter deeply. We are the stewards of a rare and beautiful phenomenon, conscious life. Our choices shape not only the future of humanity, but the legacy of consciousness itself. The stars may burn for billions of years, but without someone to witness them, to wonder at them, to tell their stories, they shine in vain. This awareness challenges us to think long-term, to see ourselves not only as individuals or nations, but as participants in a story that stretches across billions of years. We are not just inheritors of the past, we are ancestors of the future. The technologies we develop, the environments we protect or destroy, the values we cultivate, these will echo long after we are gone. Cosmic exploration instills a kind of intergenerational ethics, a commitment to preserve and expand the domain of life, thought, and creativity in a universe that does not guarantee their survival. That means protecting our planet, advancing our sciences, and preparing to take our first careful steps beyond Earth, not to escape responsibility, but to extend it. Yet for all its grandeur, cosmic exploration is also a personal journey. It invites each of us to confront our own questions. Who am I in the face of the infinite? What do I believe? What will I contribute to the story of life and understanding? These are not just scientific or philosophical questions, they are spiritual ones. Not in the sense of religion, but in the sense of deep meaning. The cosmos, after all, is not separate from us. It is within us. The calcium in our bones, the iron in our blood, the oxygen we breathe were forged in ancient stars, billions of years ago. The atoms of your body were once part of stars, oceans, and clouds. You are the universe, rearranged into a form that can ask questions. This realization transforms the way we see life. It elevates the everyday. It reminds us that consciousness is not a trivial accident. It is a rare form of order in a vast sea of entropy. It means that every act of kindness, every pursuit of truth, every moment of wonder is a continuation of the cosmic story. We are not just observers, we are participants. We are not just learning about the universe, we are the universe, learning about itself. The journey into the cosmos is, in the end, a journey inward. The telescopes we build, the equations we write, the questions we ask, they all reflect the deepest longing of the human spirit, to belong, to understand, to be more than dust. And that longing is not weakness, it is strength. It is what drives every discovery, every breakthrough, every new frontier. It is what lifts us from instinct to insight, from survival to civilization, from the cave to the stars. The balance between knowledge and mystery is not a tension to be resolved, but a harmony to be embraced. We need both. Knowledge gives us power. Mystery gives us purpose. Knowledge builds tools, mystery builds meaning. Knowledge tells us what is mystery, asks us what could be. Together, they form the twin pillars of progress and wonder. Together, they guide us toward a future worthy of our curiosity. So what is the final moral lesson of cosmic exploration? It is that the universe is not just a place, it is a process. A process that began in fire and silence, evolved through stars and atoms, and now speaks in questions and dreams. We are part of that process. We are its voice, its mirror, its child. And our task core, sacred taskies, not just to survive, but to understand, to learn not only how the universe works, but why it matters that it does. To ask not only what lies beyond the observable edge, but what lies within the human soul. In doing so, we honor the cosmos. We make meaning from matter. We turn stardust into story. And we fulfill the greatest possibility of all, to become not just intelligent observers of the universe, but wise caretakers of its wonder. That is the gift of curiosity. That is the legacy of science. And that is the enduring moral truth of the stars. In the end, as we stand at the edge of all we note, the boundary between comprehension and imagination, the question becomes not just what the universe is, but how we should relate to its mystery. Should the story of the cosmos aim for a closed conclusion, a final theory, a complete and elegant answer that ties every thread into a singular, resolved narrative? Or should we embrace an open-ending one that acknowledges that some questions may never be answered, and that this, in itself, is not a failure, but a feature of the grandest story ever told? As science brings us closer to fundamental truths, we are simultaneously reminded of how deep the unknown truly runs. The more we see, the more we realize we are peering into an ocean with no shore. And maybe that's the point. Maybe the highest purpose of cosmology is not to close the book, but to keep it open for generations to come, for the endless pursuit of understanding, for the ever-evolving capacity of curiosity. The idea of an open-ended universe resonates with the structure of the universe itself. Cosmologists now believe that the expansion of space is not slowing, but accelerating. The cosmos is not collapsing back into a final moment of compression. It is stretching outward with ever-increasing speed. Galaxies will continue to recede from one another. Stars will burn out. Black holes will evaporate. And even if all matter is reduced to cold particles drifting in darkness, space will remain infinite, silent, and unfinished. If the universe itself refuses to resolve into a neat ending, why should our intellectual journey be any different? Every answer we find, every new law, every fresh observation, inevitably opens up new questions. The Big Bang explains the observable origin of our universe, but not what came before it. Dark matter can be inferred, but not directly seen. Dark energy drives acceleration, but its essence remains unknown. Even the merging of general relativity and quantum mechanics continues to elude our best minds. These gaps aren't signs of science's weakness. They're signs of how much we have left to explore. The value of leaving questions unanswered lies in what those questions do to us. They humble us. They drive innovation. They sharpen our minds and stretch our imaginations. They prevent us from becoming complacent. Every mystery is an invitation not to retreat into myth or certainty, but to create new tools, new ideas, and new ways of thinking. They keep the spirit of exploration alive, even when the terrain is abstract, invisible, or mathematically elusive. Consider the many shifts in our understanding over time, from geocentrism to heliocentrism, from Newtonian mechanics to Einstein's relativity, from classical physics to quantum theory. Each revolution in thought required us to first admit, we don't know. If we had rushed to close the door too soon, if we had clung to old models in the name of completion, we would have missed the true structure of reality. The unanswered question is not a weakness, it's a launch pad. And yet, it is human nature to want closure. We want to believe in a final theory of everything in neat equation that explains all forces, all particles, all of space and time. We imagine such a theory as a crown jewel of human intellect, a testament to our mastery of the cosmos. But what if the truth is more nuanced? What if the universe is not a closed system with a single, complete solution, but a living, evolving complexity that forever escapes final definition? What if ultimate knowledge is not a destination, but a direction? The greatest scientists have often been the most comfortable with this ambiguity. Albert Einstein spoke of the mysterious, saying it was the most beautiful thing we can experience. Richard Feynman famously said, "I can live with doubt and uncertainty. I think it's much more interesting to live not knowing than to have answers which might be wrong." This openness to uncertainty is not a compromise, it is a profound strength. It's what allows science to grow, to revise, to adapt. It's what makes discovery possible. So, what are the biggest takeaways from our journey through the cosmos? First, the universe is vastly bigger, older, and stranger than we ever imagined. It began in a state of unimaginable energy, expanded and cooled, formed stars and galaxies, and gave Rizian at least one small planet of conscious beings capable of asking where they came from. Second, most of the universe is hidden from us. Dark matter and dark energy dominate the cosmic inventory, yet remain largely mysterious. We are living in a universe of shadows and whispers, inferring deep truths from the movements of galaxies and the flickers of ancient light. Third, our best theories, relativity and quantum mechanics, describe different aspects of reality, but do not yet merge. This suggests that something deeper awaits discovery, a more fundamental framework that unifies what now seems fragmented. Fourth, the frontier of cosmology is not only physical, it is conceptual. We are now questioning the nature of time, space, causality, and even reality itself. Is space emergent? Is the universe a hologram? Are we living in a simulation? These are no longer fringe questions. They are serious scientific possibilities. Fifth, and perhaps most important, the act of asking these questions changes us. It elevates us. It transforms scientific inquiry into a moral and philosophical journey. As we seek to understand the universe, we develop traits that transcend data: patience, imagination, humility, and hope. We become more than observers, we become co-creators of meaning in a cosmos that does not offer meaning freely. We find purpose not in what the universe is, but in what we do with the knowledge we gain. And this, more than any specific discovery, may be the true legacy of cosmology. The infinite possibilities of space remind us that we are not at the end of the story, but at its opening chapters. There are still vast regions of the universe we will never see, eras we cannot touch, particles we cannot yet detect, and questions we cannot yet frame. But rather than discouraging us, this should inspire us. We are just beginning. The technologies of the next century, quantum computing, Gravitational wave observatories, artificial intelligence, deep space missions will unlock doors we didn't know existed. The minds of the next generation children born today, watching their first star, will carry this journey forward in ways we can't yet imagine. And so, we arrive at the final question: should the mystery remain open, ended? The answer, in a word, is yes. Not because we fear answers, but because we respect the complexity of the cosmos. Not because we give up on truth, but because we recognize that truth is a horizon we move toward it, but never reach the final edge. Every new piece of understanding expands that horizon, revealing new terrain, new beauty, new wonder. The openness is not a lack of resolution, it is the resolution. It is the realization that the universe is not a puzzle to be completed, but a symphony to be played, explored, and evolved. It is the commitment to stay curious, to keep asking, and to never settle for finality when the cosmos offers infinity. In this open conclusion lies the greatest human strength. We do not need a closed book to find meaning. We find meaning in the pursuit itself. We find identity not in knowing everything, but in daring to ask anything. We are not the masters of the universe, we are its students. And if the universe is infinite, then so too is our capacity for wonder. That is the final truth. That is the cosmic inheritance we pass down. Not just facts and formulas, but the courage to look up at the night sky and ask, what else is out there? And the wisdom to know that asking is, in itself, a kind of answer. So let the mystery remain. Let the story unfold. Let the questions deepen. Because as long as we are curious, the universe will never be silent. As long as we search, we are part of the stars. As long as we dream, the cosmos will echo with possibility. And that, in the end, is more than enough.